Hello, pre-AP Chemistry. In this podcast, we're going to review the concept of chemical equilibrium and how to calculate equilibrium constants and what they mean. So let's get started. As we covered the other day, equilibrium is a condition where the rate of forward reaction equals the rate of reverse reaction. So in other words, if we have a reaction and our initial amounts of products and our initial amount of reactants change as the reaction progresses, the reaction reaches a state of equilibrium when the concentrations of those reactants and products stop changing. That's when the reaction finds its happy place and it stops changing. So the equilibrium constant is nothing more than a number that we assign to the reaction to show how far it goes to completion. So let's imagine we have the indicated reaction. X reactants become Y products in equilibrium. That's what this sign means, is equilibrium. And X and Y are the coefficients that we use to balance the chemical equation, the ones and the twos that we write in there to balance chemical equations. So quantitatively, that means mathematically with numbers, a K value, and K because in Dutch, the chemist that came up with this concept was Dutch. I don't remember his name. But in Dutch, K is our equilibrium constant, and equilibrium constants are the concentration of your products raised to the Y power, and Y is your stoichiometric coefficient for balancing, divided by the concentration of your reactants to the X power. So if we have the reaction AB yields C plus D, all with the stoichiometric coefficients W, X, Y, and Z, we'll take the products, which is the concentration of C, concentration of D, and raise those to their respective coefficients. Likewise with the reactants, where we have A raised to the W with B raised to the X. It's nothing more than taking the balanced chemical equation and writing the products raised to their coefficients over the reactants. Now qualitatively, without having to put the algebra into it, if we have a large K value, in order to end up with a large K value, the numerator in our expression is going to have to be the large number. The numerator is our products. So what this would mean, if the products are in high concentrations to give us a high K value, a high K value shows that this is a product favored reaction. So the products are in higher concentration when this reaches its happy place. In other words, the reaction is going to proceed to the right to a high degree. If we have a small k, in other words, k is less than 1, then that means the denominator of my K expression was a much larger number, which means the reactants were in a much higher concentration, which means the happy place of the reaction is on the left side. Means the reactants are the favored state of the reaction, therefore the reaction will not proceed significantly forward. A lot of times we might even say there's no reaction taking place. However, it is taking place just to a very low degree. So some important things to ask ourselves before we start plugging numbers into the equilibrium expression to calculate constants. First question is, can we measure the concentration of a solution? And I sincerely hope the answer to that is yes, considering that's what we've been doing the past few weeks. A solution is defined as a solute divided, a solute that is dissolved into a solvent. Can we measure the concentration of the gas? Well, if a gas is introduced into a large room, it does disperse, so it is the solute. The air would be the solvent. So gases can be measured in molarity, so yes, we can. However, the concentration of a solid is generally a solute, where if there is no solvent to dissolve it, or if it will not dissolve, then we cannot measure the concentration of a solid. With a pure liquid, pure liquids are generally solvents, And if there's no solute dissolved into that solvent, we cannot measure its concentration. So the answer to these two is no. We cannot measure the concentration of a solid. We cannot measure the concentration of a liquid. So therefore, we cannot put those into the K expressions because K expressions rely on concentrations. We will leave them out of K expressions. So we'll run through an example of how to calculate equilibrium constants and show what equilibrium constants are meant to show. So for the reaction N2O4 yield NO2, we have to decide first, is this reaction balanced? And the answer to that question is no, this reaction is not balanced. So very simply, N2O4 will yield in equilibrium NO2. And to balance this equation is very simple at this point anyway, and we'll just put a stoichiometric coefficient of 2 on the NO2. So now we're going to write the equilibrium expression, which is no math, just the expression. No numbers to plug in at this time anyway, so we'll just go with this as written before. The K expression, we'll start by writing K, and we're going to take our products over our reactants. It's always going to be products over reactants. Concentration of NO2, and I'm going to raise that to the power of its stoichiometric coefficient, which is the second power. And I'm going to then divide that by the reactant, which is N2O4, and its coefficient is 1, so no need to raise it to any power. So NO2 squared divided by N2O4. Now calculate the K for the reaction, so calculate the equilibrium constant for the reaction if we have the following values at equilibrium. In order to calculate, we're going to have values to plug into this expression. And those are those values. So now it's just plugging into the expression as written. So if I have NO2 squared, I'll plug in the concentration of the NO2, which is 0.012 molar. And we can leave the units out because they're going to go away anyway. Divided by N2O4, which is 0.65 molar. So now it's just calculator work. Now, order of operations is going to be very important. Even if you have a fancy calculator, no calculators will do order of operations correctly. So just take your time. There's no rush on these problems. We'll take 0.012 and we'll square that, and we have 1.44 times 10 to the minus 4. And the E in the calculator translates to times 10 to the. If we were to translate that into standard notation, that would be 0.000144. So keeping it with the E notation just kind of saves us a little work. All divided by 0.65. So in our calculator, we can keep what we have in the numerator just on the screen, divide by 0.65, and our equilibrium constant is 2.22 times 10 to the minus 4. And that is our K value. Now, that indicates a very small number, and since that is a very small number, our reaction is going to be reactant favored. That's because the larger number would be in the denominator, which we have shown in our equilibrium expression. The larger number indicates the extent of the reaction, which on the bottom we have our reactants. So a small K value indicates a reactant favored reaction. It does not proceed significantly to the right. And that is really as difficult as equilibrium constant calculations will get. But let's work another example just to be sure, and plus this way we can get some of the finer details. So for the reaction NiCl2 yields Fe in equilibrium with Ni and FeCl2. Now we'll notice we have states of matter in this reaction, which is very important. Aqueous solutions we can measure concentrations of. However, solids we cannot. And remember, if we can't measure their concentrations, we leave them out of equilibrium expressions, which will become important when we write that equilibrium expression. So write the equilibrium expression, in other words, no math, for the reaction. So we'll begin by putting K equals. And then products divided by reactants. So the only product that I'm going to include in my equilibrium expression is going to be FeCl2. So in brackets, which means the concentration of, we'll put FeCl2. And we'll put those over the reactants. So I may have misspoke before. Products divided by reactants. I'm not sure if I did or not. FeCl2 is our product that we'll include in this, and our reactant that we'll include is NiCl2. So NiCl2 is the reactant that we'll include in this. We're going to leave out the solids because we cannot calculate molarity of solids. So FeCl2 over NiCl2, and those are not raised to any powers because their stoichiometric coefficients are 1. Now calculate the K for the reaction if we have the following values at equilibrium. So now we're just going to plug in the numbers that we're given, because in order to calculate equilibrium constants, we have to be given concentrations that occur at equilibrium when the reaction is at its happy place. So FeCl2 goes on top is 0.03 divided by nickel chloride, which is 1.00, which, very easy math, 0.03 is our equilibrium constant. And since that is a small number, which is less than 1, that is a reactant-favored reaction. One might say that the reaction may not even take place because we're not going to see any evidence that it actually does. I actually did this as a lab when I first began teaching chemistry, and my students looked at me like I was crazy because nothing happened. I didn't look up to see what the equilibrium constant would be. So, if the equilibrium constant is low, the reaction is going to be reactant favored, therefore will not proceed significantly to the right. So if it were a large K, then it would proceed significantly to the right. Okay, in the next podcast, we're going to go over how we can use equilibrium constants to solve problems, and we'll do that soon. Thank you.